Start.
During this talk, I will try to summarize some of the results we have obtained in the framework of a research project, which have been carried out jointly by my department and the Naval Research Laboratory in Mississippi. And the project was supported by the Ministry of Research and the University, the Italian Ministry of University and Research, and by the Office of Naval Research. And the final aim of the project is that of improving the actual sediment transport predictor, which are used to determine the sediment transport rate generated by propagating sea waves. Indeed, the actual predictor are not so reliable as it can be thought. Um, First, let me point out what are the problems which are affected by reliable prediction of the sediment transport rate. Of course, you need fair predictions when you try to solve the stability of coastal structures, but you need also reliable prediction of the sediment transport where when you try, for example, to predict the fate of microplastic in coastal area. The actual predictors are not so good as we think. Indeed, when you study the flow generated by a propagating wave, usually you split it into an irrotational region and in the bottom boundary layer. Well, the irrotational region is described by linear, nonlinear, or numerical models, and usually good results are obtained. On the other hand, it's not, the actual knowledge of what happens in the boundary layer, and in particular when you have sediment transport in the boundary layer, is not well reproduced by the models. Let me show you, for example, these results, which have been obtained at the end of the last century in 1995. And the results simply plot here the concentration within the bottom boundary layer at two different levels when you have suspended sediments. And you see that the model at that time were unable to reproduce both the amount of sediment. You see errors which are of the order of 100%, but also the phase of the peak was not well reproduced by those models. Unfortunately, during the last 20 years, there was some improvement, but no very significant improvement. So this topic should be further investigated. We decided to focus our attention in the bottom boundary layer. So we move our attention from the free surface to the bottom boundary layer. The flow within the bottom boundary layer is mainly controlled by the Reynolds number, which is here is made with the viscous thickness of the bottom boundary layer. Of course, you can use also the amplitude of the fluid displacement oscillation, but the two Reynolds number can be easily related. Then the phenomenon of sediment transfer contain also morphodynamic parameters, which are the ratio between the grain size, the boundary layer thickness, of course, the relative density, the mobility number, and the Reynolds number of the particles. We used, in order to investigate the phenomenon, we used direct numerical simulation. I mean, we integrated the Navier-Stokes equation and continuity equation, and the code we used was able to determine even the flow around each sediment particle. I mean, we force the no-slip condition around the sediment particle using the immersed boundary approach. Of course, we were not able to consider the shape of the grains, and we assume that the grains are mimicked by just spherical particles. And the flow around the particle was solved exactly because we used Navier-Stokes equation. The only part of the model is due to the collision between the particles, and we modeled the collision assuming that there are three contributions to the force due to the collision: an elastic force, which generates a normal component; a dissipative force, which is due to viscous effects; and also the viscous effects generate not only a normal component, but also a tangential component. Of course, the computational costs are very high, so we were not able to simulate very large fluid domains. Here you have a summary of the parameters we were able to simulate and of the size of the computational box. You can easily realize that we were not able to simulate the formation of bed forms. We just consider a flat bed configuration. So ripples are not present. Let me show you an example of the results we obtained. Here you see three plots. In here we consider parameters which correspond to, let's say, medium sand. And here you see that the Reynolds number increases from 100 for 450, so close to transition from the laminar regime to turbulence. On the other two plots, you have a turbulence regime. In this plot, you have what is called intermittently turbulent regime. I mean, turbulence appears during the decelerating phases of the cycle, but the flow tends to recover a laminar behavior during the accelerating phases. Here, on the other hand, you have turbulence throughout the whole cycle. And the last plot describes what happens if you increase the size of the sediment grains. Let us see what happens. You see that at the beginning, when you consider the smallest value of the Reynolds number, you have just a few grains which move. While when you consider larger values of the Reynolds number, you see that a much larger number of particles are moved by the flow. And when you consider the Reynolds number equal to 1000, you see that sometimes the particles are picked up and go almost into suspension. While when you consider the largest particles, the particle just slide, saltate, but they are never carried far from the bottom. And you can also see here the formation of longitudinal streaks, I mean longitudinal turbulent structures, which pick up the sediment from the bottom. So this is quite typical in steady flow, but they are present also in this oscillatory boundary layer. Another point which is interesting to point out is that even at the inversion of the flow, there are still grains which move. I mean, the sediment transport rate does not vanish. It does not almost vanish at any phase of the cycle because of grain inertia and because of the pressure gradient which drives the flow. Now let us see at the detail of the results. The first slide shows you that the simulations are reliable. They reproduce nicely what happens, what is observed in the laboratory experiment. Indeed, you see here a plot of the sediment transport rate versus the Shields parameter. The dashed dotted curve is the sediment transport predictor of Wang and Parker. And you see when the value of the sheets parameter is large, the numerical results will agree with this empirical curve, which is based on measurements, on laboratory measurements. However, when the sheets parameter is decreased, and in particular when it becomes smaller than the critical value for the initiation of sediment transport, you keep observing some sediment moving. So in principle, you never observe a vanishing value of the sediment transport rate. However, it is also necessary to point out that the value of the sediment transport rate you observe for this value of the sheets parameter is 3 orders of magnitude smaller than that observed when the sheets parameter is that assumes the largest value. So in principle, let's say that it's likely that in laboratory it was difficult to measure this value of the sediment transport rate. Here you see the details of the curves for a small value of the Reynolds number. In this case, the Reynolds number was 128. So the Reynolds number falls in the laminar regime. And you see that here you have this typical form of the sediment transport rate plotted versus the sheets parameter. When the sheets parameter is large, again, you can see that the numerical results agree with this empirical law, which was proposed by Grasser and Ayoub to determine the sediment transport rate under a laminar flow. However, when the sheets parameter decreases, again, you see that the sediment transport rate does not vanish even when theta tend to assume very small values. On the other hand, it tends to become quite small, the sediment transport rate, for a value of the sheets parameter, which is not the smallest value. But the sediment transport rate tends to vanish for this value because in this case, you have a balance between the pressure gradient, which drives the sediment particle, and the grain inertia. Here you see the sediment transport rate, which is plotted versus the phase of the cycle. Here you see the bottom shear stress, which is sinusoidal because here we are considering the laminar regime. And you see the nonlinear relationship between the shear stress and the sediment transport rate. Here you see the similar results for 3 different values of the Reynolds number. When you consider the smallest value of the Reynolds number, you have a laminar flow. But when you consider the Reynolds number equal to 450, you see that turbulence starts to appear and to affect the sediment transport. It is interesting to point out another aspect of the results because the code was able to compute the interaction between the particles and the flow. So in principle, you can have different contribution to the bottom shear stress. You have the contribution to the viscous effects. You have a contribution which is due to turbulence, because for this value of the Reynolds number, you have turbulence. And you have a contribution due to particle-fluid interaction. It's interesting to point out that for this value of the Reynolds number, we are close to what is called the intermittently turbulent regime. I mean, turbulence appears, here you can easily see that there are turbulence fluctuations, but it appears only during the decelerating phase of the cycle. Then the flow tends to relaminarize during these phases. And this is quite peculiar of the oscillatory boundary layer, in which you have, for relatively small Reynolds number, you have a relaminarization phenomenon. Another interesting results which have been shown by the simulation is that the behavior of moving sediment is different from the behavior of the same bottom configuration, but with the particle fixed in the initial position. For example, here you see that the Reynolds number is the same in these two simulations. The grain size is the same, and you obtain quite different results of the bottom shear stress. The differences between the two plots is that in this case, the particles are kept fixed in their initial position. On the right, you have the results when the particle moves. And you see that there are very large differences in the bottom shear stress in the two cases, even though the parameters, the hydrodynamic and morphodynamic parameters are the same. So it can be concluded that moving particles have a large effects on turbulent structures. Here you see, for example, the behavior of the kinetic turbulent energy for two runs. It is interesting to look at these two broken lines. One is the elevation of what we call the resting bed. I mean, you have the maximum elevation of the particle which do not move. Only the particle which are on the surface layer moves. So only the particle which are above the resting bed elevation move. But you can define sorry, you can define the bottom surface looking at the concentration which assume a value equal to 0.1, and above this level you have still moving particles, but they do not belong to the bottom. Here you can see the results of the simulation plotted along with other experimental measurements, which measure the oscillation of the resting bed during the wave cycle. I mean, when you consider an oscillatory flow, the sheets parameter changes, so you have different elevation of the resting bed during the cycle. And these are the experimental results, and these are the results of our numerical simulation. And these are the results, similar results, which show the, let's say, layer of the moving particle, the thickness of the layer of moving particles. If you keep increasing the values of the Reynolds number, or if you decrease the size of the particle, the particles tend to be carried out into suspension. The presence of suspended the particle can be seen by comparing the results of these in this plot with the results of in this plot. Indeed, here you can easily see that the amount of particle, I mean the sediment transport rate, I mean the amount of particle which move during the accelerating phases are quite different from those during the decelerating phases, even for the same value of the sheets parameter. What does it mean? It means that there are effects related to the pressure gradient, certainly, because effects due to grain inertia, but also the largest contribution of these differences is due to the fact that once the particles are picked up from the bottom, they take some time to fall down again to the bottom. So the delay, because the differences between the accelerating phases and the decelerating phases are due to the time required by the particle to settle down again on the bottom. Here you see further results. on the thickness of the layer where the particle move. You know that there are a lot of experimental data on the thickness of the so-called saltating layer, where the particles saltate, and these results are only obtained during in steady flows. And this black line is the empirical curve which has been proposed to describe the height of the saltating layer in steady flow. And you see that when you consider a relatively small value of the Reynolds number in large particles, the maximum distance attained by the particle during their trajectory, it's well reproduced by this curve, which was obtained in steady flow. However, when you decrease the size of the particle, a lot of particles tend to attain largest distances from the bottom. I mean, you see that here the distances are larger than that predicted in steady flow and of the saltating particle. And if you decrease the particle again more, you see that the particles start to be transported in suspension. So let's say here you have a bed load, here you have a suspended load, and here you have the transition, since of course in nature you have always a continuous phenomenon. You have a transition between the bed load to the suspended load. One of the problem that you face when you try to predict the suspended load is just to find a good relationship to be forced as boundary condition. Indeed, it's well established that sediment concentration can be determined by means of an advection diffusion equation, where you add this term to take into account the fall velocity of the sediments. So this equation can be easily integrated. The key point is, what is the boundary condition which should be forced? You know that usually a boundary condition is forced at a reference level, which is assumed to be twice the grain size. For example, Fretzo and Degar propose as a reference distance from the bottom where to apply the reference concentration equal to twice the grain size. However, it's the empirical predictor of the bed load assume that all the particles which move in the saltating layer contribute to the bed load and not to the suspended load. So it seems to us that the reference concentration should be forced at a distance from the bottom, which is not twice the grain size, but which is the upper part of the saltating layer, or the saltation layer. So let's say that we propose to use as a reference level this empirical formula, which is mainly based on the thickness of the saltating layer. And the numerical results suggest that during the accelerating phases, you can use the typical relationship proposed for steady flows. But during the decelerating phases, you have to force let's say, a almost constant value, which is the maximum value attained during the accelerating phases. Of course, if you compare these coefficients with those proposed, for example, by Fretzo and Degar, you see that the values of L and A are different from those which can be found in the book dealing with sediment transport. But the smallest value are due to the fact that the reference concentration is forced at a distance which is not close to the bed, but it's the thickness of the saltating layer. Okay, thank you very much for your attention.
Thank you very much. Very interesting. Are there any questions from the audience? See, so I have a very naive question. Could you have also sediment transport by non-viscous effects? You know, I remember there's a old paper by De Silva and Peregrine where they have, you know, sort of shear flow, and then in connection with the wave motion, the shear flow actually creates non-monotone pressure, which is larger at the bottom than, you know, further up. So has that been considered at all?
The flow is driven by a pressure gradient which is constant in the vertical direction. I don't know if you made this question. I mean, the thickness of the boundary layer is assumed to be much smaller than the water depth. So the pressure gradient does not depend on the vertical coordinate.
Right.
But this is reasonable because the boundary layer thickness is usually in the real world, the boundary layer thickness is quite small compared to the water depth. So you can easily assume that the pressure gradient does not depend on the vertical direction. I mean, it doesn't change in a thickness of a few centimeters, which is the thickness of the boundary layer.
Right. Yeah, but I mean, do you think there'd be any chance to obtain results that are in line with what is known, you know, with a non-viscous model?
What do you mean no viscous?
So, you know, basically, if you don't have a boundary layer, or, you know, you simply disregard it.
Of course, it can be, in principle, it's easier because, you know, in order to solve Navier-Stokes equation, you have to put a lot of number of, I mean, a grid size, you have to use a grid size, which should be much smaller than the boundary layer thickness and the size of the grain size. If you assume that the boundary layer thickness does not exist, I mean, if you assume a uniform flow in the vertical direction, you can use a larger numerical grid. Of course, you have to pay attention on the relative size of the grains and of the numerical grid. I mean, the numerical grid should be much smaller than the grain size, of course, if you want to describe the flow around the grains as we made.
Mm.
I mean, the numerical costs are very high because, you know, we solve the flow around each grain. So,
Right.
and the grid size was much smaller than the grain size. So
Yeah.
it's time consuming.
Yeah, I see. Are there any other questions? Okay.